The aim of today's lab work is to build a SimEvents model for the arrival and treatment of patients at the emergency stage in a hospital. Here you have, first of all, the resources. These human resources, will be the nurses in the triage section and the doctors at the doctor care section. First of all, in the flow diagram, we have the patient arrivals that will depend on time, as you will see later on. Then we have the triage section. Here, all the patients are assigned a color depending on the severity of their illness. You will see later on. Then we have this result of this classification of all the patients. And then we have the doctor care. First of all, you must know that at the emergency stage in a hospital, as a result of the triage process, every patient is assigned a color depending on the severity of his or her illness. The most critical is the red one, then immediately after we have the orange, the yellow, the green, and the blue one, it means that there is no severity of patient's illness. Here you have the flow diagram that tells you all the questions that someone must ask herself in order to tell, as a result, the corresponding level of the illness of the patient. First of all, in order to manage the arrivals of patients and in order to tell how many human resources there are in every shift, we must deal with the working shifts. As you can see here, the simulation will last 24 hours, 60 minutes per hour, and 7 days. So that product will result in the total length of the simulation time. First of all, here we have the clock time, and this is the shift length in minutes. As you can see, 12 hours multiplied by 60 minutes. I divide this in order to have numbers between 0.0 until the last one, that is 14. But here you can see that I have applied a floor rounding function in order to have integer numbers here. Here I will have 0, 1, 2, 3 till 13. And at the end I add 1 in order to turn these numbers into 1, 2, 3 till 14. 1 will be Monday AM, 2 will be Monday PM, and so on until 14, that will be Sunday PM. The resources will depend on, the resources at the doctor's care section will depend on the color. As you can see here in rows, you have the different colors. This first row is the red color, red doctors. Here we have the orange ones. Here we have the yellow ones, the green ones, and the blue ones. As you can see, the blue ones and the yellow ones are the small numbers here. The small numbers are in here. Why? You will see later on. This table is for AM shifts, and for PM shifts we have this other table. For the nurses are in charge of the triage process. They both can do all triage tasks. One nurse is at full time, the other one is at part-time on Fridays, the AM, as you can see, the AM shift, on Saturdays for the AM shifts, and on Sundays for AM and PM shifts. As you can see here, I have gathered all together, all the resources together. Can you see here the nurses? The nurses, yeah, that's the nurses resource pool. And then here I have all the doctors. These tables, all these tables have been gathered together in rows. Here for the green ones, the yellow ones, and so on, in a lookup table. What about the patient's arrival? The patient's arrival is an exponential probability function. Here you are. Can you see here? I take a random number with an exponential probability distribution function, and you will see later on how I use this MATLAB function. These are all the means. This is the mean time between arrivals. They are exponentially distributed, and as you can see here, there are 11 minutes as a mean between one patient and the following one in the AM shift for Monday. As you can see, the smaller the number, the more frequent are the arrival of patients. As you can see here, I have a lookup table with the mean values for this exponentially. These mean values depend on time. So here we have the shifts. Then depending on the shift, the number will be a different number from this table. And then here I have a MATLAB function. This MATLAB function takes the input, this U, as you can see here, and the output is a random number exponentially distributed with an input of U, depending on the mean. So this here is the mean value for this exponential. The triage section. The triage section, first of all, entities. Here we have the entity. This entity gets in an acquiring block, acquiring resource acquire block, and we acquire here a nurse. As you can see here, here I have all the list of all the resources, and nurses are here, and I need one nurse. Here there is the server, is an n server with n equal to 2, because here I can assist 2 patients at the same time. As you may remember, we have 2 nurses, for example, on Sundays. So both nurses can do the work. So we have 2 patients at the same time being assisted. Here we have an event-based random number. It's a uniform distribution that takes between 5 and 7 minutes to assist a patient in the triage section. Then I release the nurse here, okay, and the entity gets out of this subsystem. Pay attention on the initial seed. There is a number for the random number generator, but here I use the clock function that tells me the year, the month, the day, the hour, the minute, the second, with milliseconds. So I take all these quantities, I add all of them, and I round them. Why I do this? Because when I run a new simulation, I want to have different random numbers. So that's why I changed the initial seed for every simulation, because every simulation happens or starts at a different clock time. What about the patient classification, the triage results? After the triage section, entities go through this block, and every patient is assigned an attribute. This attribute will be color, and this color will be 1, 2, 3, 4, or 5, being 1 the most severe illness. Here you have the probability for a patient to be graded 1, 2, 3, 4, or 5. As you can see, the smallest probability is to be grade number 3, and the biggest one is 0.4 for illness of type 4, the green ones. Well, here the patient is assigned a color, and this color is the result of a subsystem. This subsystem has been built by myself, and here we have, here at the beginning, we have a uniform random number. Uniform random number. This uniform random number goes from 0 to 1. So then here I have different blocks that are called compare to constant. Compare to constant. Well, here I have added the result of these 4 functions and 1. As you can see here, for number 1, I have a probability of 0.203. So if this number that has this range from 0 to 1 has a value under 0.203, this will be false, 0, this will be false, 0, false, and false. So a 1 will be the result of this addition. But then, if you pay attention here, if it's greater than 0.203, this will result in a 1. So 1 plus 1 will be a 2 in here. So orange patient. What about if I add these two numbers? If this random number is greater than 0.355, as you can see here that is the addition, 0.355, then this will be a 1. So it will be classified as number 3. 1, 2, and 3. 3. That means that will be a yellow one. And I go on until 0.837, which is the addition of all these quantities here. So here I have a number from 1 to 5. I translate this time signal into an event signal, and this signal, that is this signal in here, tells which color is assigned this entity, this patient. What about the patient care? For the red ones, the minimum time is 15, the maximum 13. So here I have a uniform random number, and this uniform random number has a minimum value of 15 and a maximum value of 30. As you can see here, I acquire one red doctor in here when the entity goes through this port, and then here the patient is being assisted. This is an N server. How many servers do we have in each block? First of all, here I have 1, here I have 1, here I have 2, here I have 5, and here I have 2. Why this? It's because of what's the maximum value of human resources in every section. For the orange ones, if we go back here, remember the orange ones here and here, we have a maximum of 5 doctors. 5 doctors. So that's the reason why here we have a maximum of n servers, being n equal to 5. So here we have the route for the red patients, the orange, the yellow ones, the green ones, and the blue ones. And pay attention to this block. This block is an output switch that is working on attribute. If attribute is 1, the entity that in comes to the block is being output of the block by output number 1. If the attribute color is number 2, the entity will go through output number 2, and so on. So here we are, the whole model. Here we have the shifts. Here we have the recesses. Here I have some floating scopes. About these variables in here, these are the queues, as you can see here. Here I have the patients incoming. Here I have the triage section, and here I set the attribute color. And depending on the color, on the severity of the illness, 1, 2, 3, 4, 5, here we have the red doctor care, the orange doctor care, the yellow one, the green, and the blue. At the end of the simulation model, I have a path combiner, and as you can see, all the entities go to a sink. Here I can monitor with several displays. Here I can monitor how many patients have been treated as red patients. But what's the problem of this situation? As you can see, we have here more probability of green patients than all the others. As you can see here, the green patients, this number more or less doubles this number, which is the second one in order. So at the end of the simulation, we can see that the resource use percentage is so wide. As you can see here, the green doctors are very tired because they have been working the 90% of time. They have been busy. Why? Because they have a lot of green patients. And on the other side, we have the yellow doctors, which are under the 20% of use. Why? Because they have a very small number in here, a very small probability to have yellow patients. So, what about if I share green doctors with the yellow ones and the yellow ones to the green section, in order to make this function so low and to make this function grow up to more or less the 50% of use, which will be more or less normal for this situation. Because all the doctors can do all the tasks in these sections. So, how can I do that? Well, after the triage section says that patient is number 1, 2, 3, 4, or 5, as you can see here, 3 and 4, which are yellow and green, are gathered together in a path combiner and then switched upon an output switch. But what about the switching criterion? As you can see here, we have 2 output ports, but the switching criterion is not on attribute, it's not based on attribute, it's based on round-robin criteria or equiprobable. They are not synonyms. Round-robin means one patient goes through this, the next go through this. The third patient goes again to the yellow, the fourth again to the green, and so on. But equiprobable depends on probability, 50-50. But it's not 1-to-1. It's a question of probability. More or less, it's the same situation, but it's not strictly equal. So this way, I will share yellow doctors with green doctors in order to do the treatment for both kinds of patients. As you can see, this is the before situation. This is the original one, as you can see. Very tired, the green doctors. So idle, the yellow ones. And as you can see, after this, the green and the yellow line, they are so similar, as you can see here. Yeah. And all the percentage of use of all the doctors are between the 40 and the 60%, which is absolutely correct. That was my intention with this improvement on the system. Finally, there is a last stage on this model. As you can see here I have the release for the red doctors, the orange ones, the yellow, the green, and the blues. But these numbers in here are strictly red patients. Here we have red patients, but here and here I have a mixture of yellow and green patients in both sides. As you can see, these numbers are the same, more or less the same, depending on the simulation. Okay, so, and finally, here I have blue patients. But I want to know how many patients are treated as yellow ones and how many patients have been treated as green ones, because I have both types in both sections of the model. So I gather all of them and then I split again with an output switch based on attribute. Which attribute? Again, color. And now here I put an entity sync for every severity for the patients, every color, every attribute. Finally, I put here a multiplexer in order to show all the numbers, and these are the real numbers. As you can see, 236 is this number because nothing changed with my improvement. But the numbers are so different in here, 92 and 480. Obviously, if we add these two numbers, we will have the addition of this number and this number. But as you can see here, they have been splitted into yellow patients, 92, and 480 green patients. So here, at the end, in order to have more or less the distribution of the relative values of these severities, I divide every number in this table by the sum, the addition of all the numbers, in order to have the relative quantities, as you can see here. As you can see, the results of the simulation, here we have severity 1, the red, is 0.20, which is so similar to the original probability described by the problem statement. Finally, here we have a number that is so close to the original probability of the problem. Then on number 3, more or less the same, as you can see. It's nearly perfect. Finally, on number 4, here we have the 41% of patients. And finally, on 5, 17%, which is close to 16. So at the end, the improvement of the system means the following. To put like a subsection with a path combiner and an output switch based on round robin or equiprobable. Both more or less do the same work. Finally, all the patients are gathered together in a path combiner and finally splitted again, switched again, according to the color attribute, according to the attribute criteria. And finally, here we have the resulting numbers. So what about the tasks? 2 lab sessions are needed. So more or less, you must spend 4 hours in order to build the model I have explained before. What's my interest? The report should include the percentage of use of all the resources. So I want to know the percentages in triage, about the nurses, and the doctors, on the doctor care section. As you may remember here, I have the queues. So I want this model to be built and then to be run several times. And according to these several times, several replications, you can have the probability distributions of every measure of the queue length and the mean time people is waiting in a queue. So we have the histograms. So I want this information to be in the report. Finally, what I want is to share doctors in these 2 different areas. So, to summarize, despite what is written in the original document, I don't want extra personnel needed. I only want that you build this model with this improvement, the sharing of doctors in the yellow area and the green area. And this work must be delivered on the 19th of April. So you have more or less 2 weeks, okay, in order to do the work. Only 2 lab sessions are expected. And you have all the information in this video. I will be the 10th of April and the 17th of April in this virtual room. You can take note of that. I will be in this virtual room in order to answer all your questions. Whatever you need, I will answer it here. The 10th and the 17th. From 10 a.m. plus 2 hours, more or less. So I will be waiting for you and all your questions about this simulation model.